So thank you very much for being here. I'm very glad to present you my PhD result. So as Victor just said, my PhD subject is around extreme plasma interactions for strong field QED. So let's start. As you can see here, the plan. I will start with an introduction about theoretical concepts about QED and plasma acceleration. And then I will introduce you to the four main topics of my PhD. So let's start with an introduction. So I want to introduce QED by starting from classical physics. So as you know, classical physics is including classical mechanics, electromagnetism, thermodynamics, optics, and many other theory. And so in the early 19th century, physicists thought that physics was almost complete at that time. At this time, there were two small problems, blackbody radiation problem and Mercury's orbit, but people thought that those problems would be resolved in a couple of years. It turns out that it was not really the case, and it led to the two major breakthroughs in physics. So the first theory was special and general relativity, developed by Einstein and others, describing space-time as a dynamic object. And the second great revolution was, of course, quantum physics, developed by numerous physicists. You have some examples here, which describe particles with wave function. So this is what we call modern physics. And so since that time, the goal has been really to try to unify those two theories. So from a side, quantum physics, which is dealing with particles, the small scale, microscopic scale, and from the other side, gravity, general relativity, describing gravity at the large scale. And so finding this so-called theory of everything turns out to be very hard. So I'm sure you know the two major theory, string theory and loop quantum gravity, which tried this unification, but they didn't lead to actual results. So physicists are keep searching in that direction. So although it was not possible to unify quantum physics and general relativity, physicists came up with a unification of quantum physics and special relativity. So special relativity is describing objects moving close to the speed of light. And so this partial unification is called quantum field theory, QFT for short. So this is a wide ensemble of sub-theory, as you can see here. And so today we are going to focus on just a fraction of this QFT, which is called quantum electrodynamics, QED for short. And so QED can be thought really as a quantum and relativistic version of electromagnetism. So the two great contributions in QED were firstly by Paul Dirac, the Dirac equation, which really described the particles, so electrons, positrons, and quarks, and their interaction with the photons. And on the other side, the Feynman diagram, which describes some quantum physics scenarios, and many others contributions. So in QED, a typical scenario is the interaction between an electron in blue and a photon. And so QED will answer simple questions like, what is the probability of the interaction, or what is the outcome of this interaction? So for example, a possible scenario is that the electron absorbs the photon, and then will re-emit a photon a bit later. For instance, this process is called the Compton scattering, and so this is the Feynman diagram of the Compton scattering. So it turns out that those diagrams are much more than simple drawings, because you can associate to each line and vertex a mathematical term. And so if you want to know the probability of this process to happen, you just multiply all the terms together and you have the probability. So it's a very powerful tool to calculate some quantum physics scenarios. So with this tool, physicists have been able to calculate some numerous scenarios. You can see here a couple of examples here. And to calculate some experimental observables from this scenario, so probability rate and cross-section. And so maybe the most famous example of this is the calculation of anomalous magnetic dipole moment, which was calculated to an incredible accuracy, making QED the most precise theory ever tested. So now, what is strong field QED? So as before, we are dealing with particles, electrons and positrons, but now in a strong electromagnetic field. So this theory is relevant to describe, for instance, what is happening in astrophysics, in black holes, gamma ray bursts, magnetars, where you can have very strong electromagnetic fields. But very recently, it's also very relevant to describe what is happening with very intense lasers, the petawatt laser facilities that are being commissioned all around the world. So in a typical strong field QED scenario, you have this strong electromagnetic field, which can come from laser, astrophysical object, beam self-field, and so on. And you can have an electron which is in this background field. The problem now to describe the electron is that it will interact with a lot of photons from this background field. So it's very hard to describe with the standard tools of QED. So what physicists have came up with is what they call the dressed state. So it's basically describing the electrons together with this electromagnetic field. You can see here an example of mathematical expression of a dressed state in a constant cross field. And with those expressions, physicists have been able during the years 30 to 70 to describe new processes. And so they find out that new processes were happening in this strong field. So if you take, for instance, a laser pulse and you make it collide with an electron, the first step can be an absorption of a lot of photon from the laser by the electron. And then the electron can re-emit a very high energy photon, gamma ray, a bit later. So this is called nonlinear inverse Compton scattering. And then this gamma ray in the laser field can decay into a pair of matter-antimatter, electron-positron pair in that case. And this is called the nonlinear Breit-Wheeler pair creation. So note that this second process is really a creation of matter from light, so it's very interesting fundamentally. And so those two processes were pretty hard to calculate, but physicists have come up with actual formula for the probability rates of those processes. But it turns out that now those formulas are used everywhere in the PIC codes and analytical estimations. But the derivation of those formula, if you want to learn about the derivation, is not very detailed in the literature. So now one of the side projects of my PhD, together with Arseny Mironov, have been to re-derivate the probability rate of nonlinear inverse Compton scattering. So this was pretty interesting as it's a full strong field QED calculation, and so you can really understand the deep mathematical derivation, the approximation used, and everything. So now I want to talk about how to reach the strong field QED regime. So first ingredient is of course this strong electromagnetic field that can come from a laser. But it turns out that even the most powerful lasers in the world are not intense enough to reach this regime. So if you take, for instance, an electron which is not moving, and you send a laser pulse onto the electron, the field experienced by the electrons is not high enough. So now the trick is to use ultra-relativistic particles, so particles moving at the speed of light. So in this case, the electron is moving close to the speed of light, the laser is moving at the speed of light, and in the rest frame of the electrons, the laser is being boosted locally such that the field experienced by the electrons in its rest frame is boosted by a factor 2 gamma, gamma being the Lorentz factor of the electrons. So just for you to have an idea, the gamma factor of an electron of 10 GeV is 10 to the 4. So you are really increasing the field by 10 to the 4 now. So now you can reach this strong field QED regime. So the main parameter of strong field QED is called the quantum parameter, chi, which is the ratio between the field experienced by the electron in its rest frame and the Schwinger field, which is a constant field at which strong field QED processes start to happen. So basically, if chi is well below 1, you have no strong field QED processes happening. And if chi is of the order or more than 1, you start to see some strong field QED processes. So here I wrote a quick formula to estimate the chi from the A naught of the laser and the energy of the electrons. So if I draw a timeline of strong field QED, it's pretty interesting, as you can see. So the theoretical development, as I was saying, was made during the 30 to the 70. So I write a couple of examples here. But there is really a need for testing the theory experimentally. The problem is really to reach this chi equal 1 or above is really hard. So for instance, taking the formula I just wrote before, you will need A naught equal 8 or more and more than 10 GeV of electrons energy. So it's very high. And as a result, there were not a lot of experiments that probed strong field QED experimentally. So the only experiment ever that observed positrons was the SLAC experiment in 1997. They used 47 GeV of electron beam and A not equal 0.5, and they reached K equal 0.3, so not very deeply into the quantum regime. And since then, we have a lack of experiments. But luckily, we have the petawatt lasers, which are being commissioned everywhere in the world. So pretty recently now, we have a lot of experiments, more and more, reaching those strong field QED regimes. So I won't cite every experiment, but in 2018, we had the Cole-Poder experiment, reaching again K equal 0.3. And since then, a lot of experiments are being carried out in the same range of K. So you can see that right now, it's a very important moment for strong field QED, as it's the first time we can finally probe this regime experimentally. So the number of studies in this field is really growing exponentially. So now, if we want to have high energy particles to probe strong field QED, the standard technique is to accelerate them with a conventional accelerator. So in this case, the electron is passing through cavities in which longitudinal electric field is accelerating the particles every time it passes through a cavity. And so you can have a growing electron energy with the propagation distance. The only problem with this technique is that the acceleration efficiency is around 10 MeV per meter. So if you want very high energy, you need very big machines. So LHC 27 kilometers and SLAC 3 kilometers. So an alternative technique was developed in 1979 by Tajima and Dawson, which is called laser plasma acceleration. So it's a very historically significant topic for LOA. So we remember, of course, the Dream Beam Nature cover in 2004. And now experiments are being carried out in the lab in Salle Jaune, Salle Noire, Salle Orange. And we can also cite the next generation at LOA of laser plasma acceleration, Laplace, which will look at high energy and high repetition rate. So the basics of laser plasma acceleration are the following. You send a laser onto a gas, and so the laser will ionize the atoms such that you create a plasma in which electrons are free to move. So here is a simulation of a laser plasma acceleration. The laser is coming from left to right. So it's chasing electrons on its path such that electrons are pushed from the laser path. Concerning the ion in plus here, they are very heavy, so they are not deflected by the laser pulse. So you end up with a cavity at the back of the laser without electrons. So in this cavity, you can have very high electric fields that can accelerate some particles. So if we want to plot the accelerating field, it looks like this. And so you can see that if you put a particle at the back of this bubble, here, an electron, for instance, it will experience a very high accelerating field. And so it can be accelerated pretty strongly. What is interesting with this method is the acceleration gradient, which is much more than in conventional accelerators, 10 to 100 GeV per meter here. So with the development of such accelerators, it can allow us to have the same energy but shrink the size of accelerator from kilometers to centimeters or meters. So now generating GeV electrons is really well mastered with this technique, and we can cite the recent study where they managed to produce 10 GeV electrons from such an acceleration scheme. So it starts to be relevant for strong field QED studies. So let's now present the 4 topics of my PhD. So the 2 first topics are using laser plasma accelerators. One is experimental and one is simulations. And the 2 last ones are using conventional accelerator, RF accelerators, and beam safe field, and again, one experimental and one simulation project. So let's start with the first one, Compton photon at the GeV scale from collision with a plasma mirror. So this experiment took place at the beginning in Apollon. So the goal of this experiment is to generate some very high energy gamma rays from electron laser collision. The setup is the following. So we use the Apollon laser, 15 joules, 800 nanometers, 25 first of second, and 1 shot per minute. And we shoot the laser, we focus the laser into a gas jet to create a plasma. So here we use a gas mixture to inject electrons via ionization injection. And then we place a plasma mirror, so a foil at the end of the gas jet. So here you can see a photo of the setup. You can see the gas jet. The laser is coming from the left, and it accelerates electrons, and then you can see the foil in orange here, which is actually a plastic foil. So the setup is the following. When the laser and electrons reach the foil, the laser is reflected, as in the case of a mirror, and then it collides back with the electrons just behind to create inverse Compton scattering, so it will generate some gamma rays. So the gamma rays are emitted in the direction of electron beam, and so the electrons and gamma rays are crossing the foil. So now the question is, would this scheme be suitable for strong field QED studies? So I want to compare this scheme with the classic scheme where two lasers are used. The first laser is used to accelerate electrons, and the second laser is focused to collide with electrons. The problem with this scheme is that you have some shot-to-shot fluctuation, and so aligning micron-scale electrons and laser is very hard. So in comparison, in our scheme, the electrons and laser are really close. So the laser cannot miss the electrons. So you have this auto-alignment. So it's very great for a good stability of strong field QED studies. So now after the collision between the electrons and laser, electrons and gamma ray pass through the foil, and we place a dipole which will deflect electrons regarding to their energy. They end up on a LANX screen, and so we can have the information of the electron spectrum, so energy and divergence here. The gamma rays are not deflected by the dipole, so they go straight, and they end up in two diagnostics for gammas. The first diagnostic is the gamma LANX, which allows us to know the basic divergence and shape of the gamma ray beam. And there is also a LISO, which allows us to know the energy spectrum. So this is a photo of the setup. You can see the laser beam axis, the interaction chamber, and the dipole spectrometer. So let's look at the results. So here are the electron spectra from the laser plasma acceleration. So you can see 1.5 GeV of energy, 19 picocoulomb, 3.7 millirad of divergence. And so now, if I want to illustrate this, the auto-line setup, I can look at the gamma LANX, which is looking at the collision, the gamma ray from the collision. So if I represent successive shots here, you can see we have really 100 collision rate success. So if I compare to the latest experiment where they used two laser beams, they have a few % of collision rate. So it's a great advantage. Just a sanity check, if you remove the foil, you don't have a collision anymore. So this is what you end up with your screen. There is a background signal which is coming from Bremsstrahlung, but it's very negligible. So now an interesting thing is to vary the position of the foil longitudinally. And so we will trace the integrated signal on the gamma LANX on this graph as a function of the foil position. So here, if you place first the foil very upstream inside the gas jet, you are here on this curve. So in this case, the electrons don't have time to properly accelerate, so they have a low energy. The laser is pretty intense, but then the Compton signal is pretty low. Then if you put the foil a bit further, a bit downstream, the electrons now have enough time to accelerate, so they have high energy. The laser is pretty intense, so you have an optimum of your signal here in blue. And if you keep placing the foil downstream, at some point you have high energy electrons, but the lasers start to diffract, so the intensity drops, and the Compton signal is also dropping. So now let's look at the most important result, the energy of the gamma rays. So they are measured with a LISO detector developed at Luni. So the basics of this detector is the following. So the gamma ray is crossing from left to right, the detectors, and it's being absorbed in the detector. So here you can see 3 simulations for 3 different energy of gamma ray. And you can see that the maximum is moving from the beginning to deeper inside the diagnostic as you have more and more energy in the gamma rays. So you can really, from simulations, you can really reconstruct the gamma ray spectrum with this diagnostic. So let's look at the results. Here is the measured spectrum after the collision at Apollo. In black, you can see the spectrum of the gamma ray here. and in blue and red the simulations, the corresponding simulations. So you can see here that the energy is pretty high actually. So the gamma ray reached a critical energy of 0.1 GeV. And so it turns out that we also did the exact same experiment at the ILANP facility in Romania, where we used the 10 petawatt laser to collide with electrons. So here are the electrons we got, so around 4 to 5 GeV in that case, so much more energetic. Again, we looked at the successive shots, so the signal is pretty stable again. And so this is the result. You can see now that the maximum is deeper inside the detector, and so the corresponding spectrum here exhibits gamma rays at the GeV scales. So the critical energy is 0.5 GeV, but you can see that gamma rays are produced even at more than 1 GeV. So it's pretty interesting that in this graph, because you can see that if we do simulations with two different models, a classical model and a quantum model, here in green and red, we can see that the two curves are not superposed. So basically, we think that quantum effect may start to play a role at this very high energy. So it's pretty interesting. So to summarize this experiment, it's a big step towards a PIC-QED experiment. So we demonstrated that a single laser can produce a 100% collision rate with gamma rays in the GeV range, and that quantum effect may start to be visible. So it's very nice first study. So now I will present you the result of a simulation study which basically takes the exact same scheme, but now we will add a second gas jet after the first one. So now, again, pretty similar to before, we shoot a laser. So now we want to show the potential of this scheme. So we take pretty optimistic laser parameters, 100 joules, 20 femtosecond. It leads to almost 5 petawatts of lasers and an A0 to equal 4 to start with. So again, we have this gas jet. In this case, we take a much longer plasma, 40 centimeter. So note that it's not that crazy since the recent experiments show a plasma in the 30 centimeter range. This is the density on axis, and then we have a parabolic profile of the density to guide the laser through the gas. And so we use a downramp injection scheme of 200 microns to inject the electrons inside the cavity. So this is a simulation made with FVPIC of the electron injection. You can see the laser here. So when the laser enters the gas, you can see the electrons at the rear of the cavity that are injected. So those are the typical beam parameters that we get. So after being injected, the electrons are being accelerated. So here you can see a simulation in high pace here. And so the typical electron spectrum we get as a function of propagation here is reaching 11 GeV after the 40 centimeter of acceleration. So now, instead of putting directly the foil as before, we put a second gas jet, a pretty high density gas jet, 100 times higher in density. So this gas jet is used to basically self-focus the laser. So as you know, if we have a high density, the laser will decrease in size and increase in intensity. And so when we place the foil, after, the laser will be much more intense. So the collision will be more intense. So here is a simulation of the second gas jet. So you will see that the laser will be self-focused. Concerning the electrons, they have a very high energy, so they are not too much disturbed by this high density plasma. And so you will see that the A0 of the laser is going from 4 initially to 40. So it's really an increase by a factor of 10. So 2 orders of magnitudes in intensity, actually. So here you see the simulation. The laser will shrink inside. It's being self-focused. Then we stop the simulation window, and the laser will reflect on the right side of the simulation. It's the plasma mirror. And so it will collide back with the electrons just behind. So keep in mind that this is a fully QED PIC simulation. So we have the QED physics implemented. So here, the collision between the 11 GeV electrons and A0 equal 40 laser will lead to chi equal 6, pretty deep quantum regime. And so we have the generation of gamma rays and electron-positron pairs in that case. So if we look at the spectrum of the particles that are emitted, the gamma and the electron-positron, this is what it looks like. So spectrum as a function of energy. The blue curve is the gamma ray spectrum, going all the way up to the initial electron energy, 11 GeV. And then the red dotted curve is the positron spectrum at emission. And you can see here that the positrons, where they are emitted, they are being slowing down by the lasers. So their spectrum is peaking around 3 GeV at the beginning, and it will be shifted down in energy by slowing down with the laser, so that the positrons we will measure will be at lower energy. So we also can say that some second generation gammas are emitted from the pairs inside the collision. And so the total positron charge generated is 40 picocoulomb, so a lot of charge. From the 140 picocoulomb electron beam at the beginning, it's 20% of the charge which have been converted, so it's really easily measurable. So to summarize a bit on this scheme, it's actually a very interesting scheme, because you still keep this auto alignment, but now you boost the laser just before the collision. So you can have a boost in intensity by 2 orders of magnitudes. So in turn, it will boost your chi factor by a factor of 10. So you can really reach chi above unity. And so you only need a single laser instead of 2 lasers, so it's a bit simpler. So we hope that this experiment, this scheme, will be implemented in the next run pretty soon, in the next few months. So those were the laser plasma acceleration scheme. So the results are great. It's pretty promising. Now I want to show you a bit the work I've been doing with conventional accelerators. So now we will look at collision between a beam coming from accelerator and a multifoil target. So if you take an electron beam, the first force acting on the electrons is the electric force, the Coulomb force. They repel each other. You can think of this force as an electric field living all around the electron beam. And so the global contribution of this field is to defocus the electron beam. Now if you take a moving electron beam, it will create an electrical current, which is a source of magnetic field. So you have also a magnetic field living all around the electron beam, creating a focusing force on the electron beam. And so it turns out that for ultra-relativistic beam, the magnitude of the electric and magnetic force are exactly the same, almost the same, and so they are just opposite in sign, so that the total contribution will cancel, so that at the end there is no force acting on the electron beam in vacuum. However, if we put a metallic foil, the situation changes. So at if the beam collides with the foil, at the foil surface you have the boundary condition. So the electric field must be 0 at the foil surface, while the magnetic field can be doubled at the surface. So now we have lost this balance in between the electric and magnetic force. Now the magnetic force is taking advantage. So we have this focusing effect coming from the magnetic force at the surface of the foil, such that after the foil, the beam is getting focused. So now the idea is, why don't we put many foils one after the other to increase this effect? And so it has been published in a simulation paper a couple of years ago. So we showed that taking 20 foils, aluminium foils spaced by a certain distance, you can really focus the beam to extreme beam densities. And so in this case, the electron parameters were pretty optimistic, and we showed that you can enter a strong field QED regime in that case. So, so here, even if we don't have the same parameters as in simulation, this focusing effect is very interesting, so we want to do an actual experiment to look at this effect, as it has never been observed in the past. So to do the experiment, we need these several foils, layers, and you need to send an electron beam onto this multifoil. So here we use aluminium foils of a very thin aluminium foil, around 1 micron thick. We space them by 100 microns. And you can see that when the electron is passing through the foil, it will damage the foil locally. So in order to keep the distance in between the foil pretty constant, we build what we call spacers, which are basically in stainless steel with holes inside, so of 1 millimeter of diameter. And so we put those spacers in between two foils to maintain a constant distance. And so like this, we make basically a sandwich of foils and spacers. And when we want to shoot at this multi-foil target, we can basically shoot at a hole, it will damage the foil, and then to take statistics, we shoot at many, many holes. So here you will see a 3D view of the targets on the right here. And you can see here pictures of me mounting the targets, hundreds of aluminium foils. Believe me, it's quite a pain. So in order to do the experiment, we wanted to have some pretty high electron beam parameters. So we made the choice to install this target at the SLAC experimental area in facet 2. So the facet 2 area uses the second kilometer of the total LINAC. And so here are the typical parameters we have. So compared to before, you can note that the parameters are really much more relevant here. So 10 GeV of electron beam, a charge which is 1 nanocoulomb, 1.6 nanocoulomb, and 30 microns of beam size. So let's look at the experimental area once the beam is fully accelerated. So you can see a picture of the tunnel. So the beam is going from left to right. So the first thing we have in the tunnel is the interaction chamber, so a vacuum chamber. The beam is passing through. And so in this chamber, we install our famous multifoil target. So here we have several of them, 111 foils, 40 foils, 60 foils, and 20 foils. After being focused by the multifoil, the beam is getting imaged by quadruples, which are basically somehow lenses for the electron beam. Then we have a spectrometer dipole, which allows us to know the energy axis of the electron beam. And then the beam scratches onto the diagnostic table that you can see here. You can see a 3D view from above. So we have many diagnostics here that I won't detail, but the two main diagnostics using here are called the DT-OTR. It's basically some OTR screen, which allows us to see the electron beam on it. And so in this picture, the vertical axis is the energy, and the horizontal axis is the beam divergence. So here, in order to expect, to know what to expect from the experiment, I did a simulation with the actual parameters we have at SLAC. So you can see here the beam going through the multifoil. This is the result of the simulation. You can see the beam size as a function of propagation here. The multifoil is in pink here. So you can see the blue curve. When there is no foil on the beam path, the beam just goes and drifts in vacuum. While when you put some foils, in this case 40 foils, the beam, this is the orange curve, the beam is getting focused after the multifoil, pretty much like a lens in optics, and then defocused quite strongly. So this is actually pretty interesting because you can see from the simulation that the divergence of the beam is growing by a factor of 10 in between no foils and foil case. So this is a factor of 10 is really easy to see. So what we will start with in experiment is trying to measure this increase in divergence of the beam after the focusing. So here are the experimental results. We represent the beam charge per angle as a function of the particle angle. So you can see here that the curve in blue here, in dark blue, what I call vacuum is the case where there is no foil. So the beam is really located around a particle angle of 0. And when you put more and more foils, so 20, 40, 60 foil, the beam is getting spread out, so its divergence is increasing in that case. So note that this plot is coming from actually a lot of statistics. Those are what we call waterfall plots. So in those plots, for instance, the one on top is with no foil. One line corresponds to only one shot. And so you can see here that we have a lot of shots, so a lot of statistics. And so those curves are really coming from averaging over all the shots. So you can see here that indeed the divergence increased from 75 microrad in vacuum to more than 100, and then it keeps increasing with increasing number of foils. A phenomena that we don't want to happen here is the multiple scattering. So when the beam goes through a foil, it will basically be scattered by the atoms inside the foil. And so this also increases the divergence of the beam, but it spoils the beam in a bad way. So by taking very thin foils here, more than 1 micron, less than 1 micron, we ensure that the contribution for multiple scattering is very low, pretty negligible here. So if I represent the values of divergence in a plot, here you can see the divergence in vertical axis and the number of foils in horizontal axis. So those are the corresponding points. We want to compare those points with the simulations we've been doing. So the simulations are the blue curve here, is the blue curve. So you can see that the points align pretty well with the simulation. You have the parameters up here. And then the problem is that when you focus too much your electron beam, it happens that then it's getting defocused after the waste. And so electrons at that are being very defocused will not reach the screen at the end. So you have this loss of charge, this is the red curve, when you focus too much your electron beam. So at the end it turns out that the effect is too strong to be properly measured, and so you will underestimate the divergence. So we came up with ideas to measure the divergence, estimate the divergence even with this charge loss. I won't go into detail here, but just keep in mind that for 60 and 100 development foils, the results are pretty consistent with the theory. So to summarize, I told you that putting a multifoil at the beam waist will increase the divergence after being focused. Now the question is, what happens if we shift the multifoil after the beam waist? So in that case, when the beam comes to the multifoil, it's already diverging. And I told you that the multifoil was focusing the electron beam. So this time, we expect to have a decrease of divergence because the beam gets refocused. So this is the experimental result, divergence as a function of energy. And you can see here that indeed, comparing the vacuum curve and 20-foil curve, you have this reduction of divergence. So now the question is, what if we put more foils in this stack? If we put more foil, the focusing effect will be very strong. And so now we overcompensate the divergence. So we will have an increase of beam divergence again. So here is the full result. So the vacuum divergence as a function of energy. Here are two data sets. Then we place 20 foils. As I was telling you, we decrease the divergence. Again, two data sets. But then if you keep going, you put 40 foils, you see that the curve is going up again. And then if you keep going, 60 foil, you have more and more divergent beam. For 111 foil, the divergence is really growing in that case. So you are overcompensating. So it turns out that this data is actually pretty interesting, full of physics, because during this data set, the beam was chirped. So the low energy was at the front of the beam, so here you can see, and the high energy was at the back. So this graph really shows you what's happening from front to back in the beam. And so one effect I didn't discuss yet is the fact that the focusing effect depends on whether the electron is at the front or at the back of the beam. Because when the beam collides with the foil, the electrons at the front don't have enough time to properly experience the focusing field. So the effect is pretty small at the front. And the electron at the back will see the cumulative effect of all the electrons in front. So they will see a larger focusing effect. So this is basically what we observe. If we compare, for instance, the pink curve, so 111 foil, and the blue curve, no foil, you can see that at the back, we are overcompensating, so the divergence is increasing, while at the front, we decrease the divergence because the effect is not so strong in that case. So I want to finish this presentation with showing you the potential of the beam foil collision, I would say in the future with optimistic beam parameters. So this project is called Probing Strong Field QED in Beam Plasma Collisions. So again, the setup is pretty similar as before, one electron beam and one foil. But now we take some optimistic beam parameters, so a very dense beam. Around 100 times denser than before. So we don't have those parameters yet in accelerators. So when the beam hits the foil, once again, we have those boundary conditions, so no electric field at the surface of the foil, but a strong magnetic field. But now the beam is so dense that it will produce a very strong magnetic field. And so the field is so strong that it can actually trigger some strong field QED processes. So this setup is quite interesting because if you think about it, a collision between a beam and a plasma, so the plasma will act as a mirror, reflecting the fields here. So you can see this collision as a collision between the beam and its image. So you basically replace the second beam by just a foil, a plasma. So this is mimicking the beam-beam collision, but in this case you don't have to worry about shot-to-shot fluctuation as in the beam case because the beam is by definition aligned with its own image. So here is a simulation of the beam colliding with the plasma. So we'll see the plasma is coming from the right here at the top. So as the beam is reaching the surface of the plasma, the electric field is vanishing, here you will see, and the B field is doubling. So the question we wanted to answer in this study was how high we can reach in terms of chi during the collision. So I told you the chi factor is the ratio between the field experienced by the electron and the Schwinger field. And it turns out that here we can write this E star, the field experienced by electrons, in the collision as a product between the electrons' energy, the Lorentz factor, and the contribution from the field themselves. So the self field here and the reflected field. So of course, if you want to increase E star, you can increase the electron's energy, but it's pretty obvious. So the actual interesting quantity is actually E star over gamma, so you get rid of this energy dependency. And so the paper was focusing on trying to optimize this term in blue, so basically having very high electric and magnetic fields, but keeping a good reflection on the plasma. So this E star over gamma is in black here, this is the black curve. You can see that at the beginning it's equal to 0 before hitting the foil, and then it reaches a maximum, it peaks at the foil surface, and then when the beam is inside the plasma, it goes down to 0 again. So we've been doing a parametric study to show, to study basically what are the best beam parameters to reach a very high chi. So the first beam parameter that we looked at is what we call beta, the beam shape. So it's basically the ratio between the transverse size and the longitudinal size of the beam. So here I represent the fields at the surface of the plasma. You can imagine that the plasma is on the right, as a function of time. So for instance, in the case of a cigar beam, so very elongated beam, this is the case at beta equal 0.01. And so you can see it's the black curve here. So you can see here the field is pretty short, and so the maximum of the field is reached at the plasma surface, and it's equal to 1 times the beam self field in that case. In the case of a pancake beam, so very compressed beam, this is the orange curve, so beta equal 10 in that case. So you can see here that now the field is experienced over a much longer time, and so the maximum reached at the plasma surface is equal to 2 times the beam self field, so a bit better, factor of 2. But it turns out that in experiment it's pretty hard to create some pancake beam. So actually a good compromise is to take a spherical beam, and so in that case it's the yellow curve, you have a good decent field at the surface of the plasma. So the second parameter we looked at is the beam density, actually the ratio between the beam density and the plasma, which we call alpha. So the problem is the following: if you want to have very high self fields, you need very high beam density. But if the fields of the beam are too strong, the plasma cannot shield them anymore, cannot reflect the field anymore, so they will just pass through, so bad reflection. So there is a turning point around alpha equal 1. So in the case where alpha is pretty small, you have weak field but good reflection. And if alpha is pretty large, above 1, you have a very high field, but the reflection is pretty bad. For instance, this is an example of alpha equal 3, so very dense beam. You can see that it's creating a cavity and the fields are not reflected anymore. So after doing a lot of simulations, actually, we found that the optimized set of parameters is a density alpha around 0.7, just below 1, and a beta factor of 1, so a spherical beam. So taking those optimized parameters, we did an actual PIC-QED simulation to see what's going on during the collision. So here the beam is represented in a black circle at the center here. The plasma is in blue here. The chi factor is represented in orange. So you can see it has a maximum around the foil surface. The gamma rays emitted are in yellow, and the electron-positron pairs are in blue and red. So I represent the process at 3 different times of the interaction. You can see that as the beam is crossing the foil, the gamma rays are produced, and the positrons and electrons from the pairs are also produced. So an interesting fact of this collision is that it's very fast. So the interaction time is so fast that each electrons will emit only 1 photon in average. So this ensures really clean QED signatures in that case. We can also note that the electron beam energy is pretty constant during the collision, such that at the end we can say that the outcome of the interaction, so the gamma rays and the positron electron pairs, are only determined by the initial beam parameter, which we can actually know. So this setup could really serve as a test bed for strong field QED models. So a last word about this simulation. So we can represent the chi, the maximum chi reach as a function of time. So you see that it's peaking around the foil surface. So it's reaching 25, so a pretty deep quantum regime in that case. And so during the collision, a total number of 10 picocoulomb of positrons are created. This is the magenta curve. So it's pretty easily measurable, I would say. So to summarize this setup, I would say that it's pretty suited for precision studies of strong field QED because it's very brief. It's also auto-aligned once again. And also it's much more simple than doing a beam-beam collision in which you need a collider. Here you just need an accelerator and a foil. So to conclude on my PhD work, strong field QED can be reached using high energy electrons and high electromagnetic fields. To produce high energy electrons, you can use RF acceleration, standard acceleration, or laser plasma acceleration. For the high electromagnetic field, you can produce them with beam cell field or with lasers. And so today I presented two schemes based on RF acceleration and beam cell field, and two other schemes based on laser plasma acceleration and lasers. So with the development of petawatt lasers and accelerators facility, it's really an exciting moment for strong field QED, as for the first time we will be able to finally reach the strong field QED regime at chi above 1. So we are really looking forward in the next few years to have more and more experiments in that sense. So here today I show you only 4 schemes, but there are actually a lot of different schemes proposed to study QED cascades, to use curved plasma mirrors and everything. And so I would say that the long-term goal here would be to reach this so-called fully non-perturbative QED regime at chi equal 1600. We are not here yet. But at this value of chi, we currently have no theory. So it will be very interesting to probe this regime at this value. So thank you very much for listening, and I will be happy to take questions.